All right. So let me make sure I'm recording here because my computer's giving me a weird thing. So this is the office hours for Tuesday the 15th. And so this is transformers. And basically I've gotten questions on most of the problems, so we'll be talking through most of them. Problem one. We'll start at the beginning and work our way through. So problem one, you're given a transformer circuit and you want to find the current in the line, I line, as well as the voltage across the load, V load, for the following transformer circuit when you have Vs as given. And this one is a little bit more challenging than some of them in that we have an inductor stuck in there. And so with the exception of the non-ideal transformer case, this is the only time where impedance is really going to come in. So the first thing we want to do is we want to change that 10 millihenry inductor into something of the form J omega L, where omega is, of course, 800 pi. Now, to solve this, the best way to solve it and avoid making problems in future, or mistakes in future problems, is to reflect the impedances all the way back to the source. And so what you want to do, so let me draw my transformers here for this problem. So here's my transformers. Is you want to take this 10 ohm resistor, reflect it across here using the turns ratio, which of course is 5:1. And so that would give you, I've just draw this portion. You have the inductor, the resistor, and this reflected resistor, which is going to be, in this case, N1 over N2 squared, or 25 times 10. So 250 ohms. That's what's going to reflect here. Then you need to add this impedance, J omega L, with this resistor, which is 50 ohms. So you need to add these three impedances that are in series and reflect them across this transformer, the first transformer. So reflect those across here so that, as you'll see on the next slide, you end up with some Vs connected to some impedance here. I'll call it Z double prime, like this, and then this would be your source current Is. Now technically, yes, you could reflect your source voltage here across the transformer this way. But you can only do that because there is no impedance here. There's no impedance between it and the transformer. If there was an impedance there, then you could not reflect that voltage. And since, as long as I've been teaching the course, students keep trying to reflect that voltage even when there is an impedance there, my advice would be do not reflect the voltage source across. It's only going to get you into trouble, especially on the pressure of an exam. So get out of the habit of reflecting that voltage source across now, and instead reflect these impedances across here to get this impedance. So the turns ratio here was basically 1 to 20. So we add up this impedance, call that Z1, Z2, Z3, sum them all up, divide by 20 squared, or multiply by 1 over 20 squared to get your impedance here. That'll give you your Is. Now, once you have your Is, then you know that I2 on the secondary side has to be equal to N1 over N2 times I1. So that means then I2, we can replace that by I line, has to be equal to N1 over N2, which in this case would be 1 to 20. So 1 divided by 20 times I1, which in this case would be Is. And that'll give you your line your line current. And then, of course, once we have the line current, we can use the same formula to show that I load has to be equal to 5 times I line. Because we can, once we have this Is, we can reflect it across here. So again, here's your Is, reflect that across there. This gives you your I line. The I line is the primary current for the second transformer, so you can reflect that across to get your I load. And once you have I load, you can find the voltage across the load, because you know the voltage across the load has to be the current flowing in the load multiplied by resistance, which is 10 ohms. And so that's how you would want to do problem 1. For problem 2, you need to find the length of the line that results in a particular efficiency. So you have your voltage source, Vs, which you don't know the voltage on. You have your line, R line, and that's what you're going to try to solve for. And then you have your 6 ohm resistor here. And I tell you that the voltage needed at the load is 100 volts. So we know that this has got to be 100 volts RMS. Okay? So that's the setup for part A. Now, from this, we can figure out how much current we're going to have draw. So our load current, which also happens to be the line current in this case, is going to be that 100 volts divided by 6. And that'll be in amps RMS because our voltage that we wanted was in RMS volts. Now that we have that current, we can find the power lost in this resistor. So here, E going into the load is of course going to be 1/2, but the 1/2 goes away because we're talking RMS. So it's just going to be V load times I load times the cosine of theta V minus theta I. But because everything is real, you don't have to worry about that cosine term. And so you just have the voltage times the current, which you could write, the voltage of course is going to be the 100 volts times that 100 divided by 6. And so that'll get you your power in the load. Now, we also can determine an expression for the power in the line. And the power in the line is going to depend on the resistance of the line. And so the power going into the line is going to be the current through it times the voltage across it, or another way to write that is the current squared times R line. And we want to have a certain efficiency. So we know that we want the efficiency eta be 100 times the power going to the load divided by the total power supplied, which would be power lost in the line plus power going into the load. Power going into the load we have a number for, so we know that. And so we can use this based on that. This has to be equal to what I think I specified as 85%. Yeah. 85% to find out what my power in the line should be. And so once I know the power in the line, obviously this number is going to be known, my load current is going to be known, and I can find the resistance of the line. And we know that the length of the line is related to the resistance in the line by 9 ohms per kilometer. So for a 4 kilometer long line, then you'd have a 36 ohm series load. So that you can then translate that line resistance into a length in kilometers. And so that's how you find the length of the line. And of course, once you have this current here and the resistance of the line, you know that the Vs, the voltage at the source, which you also need to find, is going to be the current flowing multiplied by that total resistance. So that was part A. For part B, you want to do the same thing, only now you have a turns ratio in there. And so you have your voltage source, you have the resistance of your line, you have your transformer here, and there's your load. The voltage here has to still be 100 volts RMS because that's still what you need. And your turns ratio is 13 to 1. And so from there, you can find once again your load current is going to be the same. But now we can reflect this load current across. And so our line current is now going to be different. Our line current is going to be the load current, I load, divided by a factor of 15. That was my turns ratio here. Now the power loss in the line is going to be the same as what we found before, but because the line current is different, that means my line resistance can be different. And once again, once I get the line resistance, then I can determine what the length of the line needs to be. Now, in terms of the voltage, though, the voltage across the source, we also have to reflect this 100 volts here across that transformer to get this, I'll call it V1. And V1 and Vs are not the same. Once you have V1, then you need to add the voltage drop across this resistor, which would be I line times R line, and that will get you then what Vs is. You could also reflect this load impedance across the transformer and then have I line times the total impedance, which in that case would be R line plus N1 over N2 squared times the R load. So either way will then give you the Vs. All right, so moving on to problem number 3. If here we have I tell you what IS is, and I tell you what VS is. And I tell you what everything else is. The only thing I don't tell you is what is the turns ratio. And so here's your VS. Here's your 5 ohms. Here's your first transformer. Here's R line. Your second transformer. And here is R load. And so you know VS and you know IS. And here's your IS. Well, and this is of course 1 to N and N to 1. Well, this problem is screaming, since I tell you VS and IS, this is screaming to find the impedance. Because you know that if I were to reflect this resistor across, add it to R line, reflect it across here, add it to 5 ohms, and drop this down here to some VS Z total, IS, that Z total has to be equal to VS over IS. And so if you reflect this load impedance across here, then you redraw the circuit that way. So here's your 5 ohm resistor, first transformer, R line, and then here would be your N1 over N2 squared. That's second transformer times R load, reflected across. Then we need to add both of these together, have that impedance, reflect it across this transformer, so that we would then have some 5 ohms, the new impedance here, which would be, in this case, N1 over N2, where now it's 1 over N squared, times R line plus this stuff. That's going to be then, this sum here is going to be my total impedance, which I know has to be the ratio of VS over IS. And from there, I can just find my turns ratio, because I know everything in the circuit except N, and so I can just solve for N. And it turns out that even though I do have an N squared bouncing around, I don't actually end up with a quadratic. I just have a single root. Actually, technically it's plus or minus that value, but you can't have a negative turns ratio, so obviously it's the plus one. So that is problem number 3. So now let's move on to problem number 4. So we want to find the current in the line and a bunch of other stuff for this transformer. 100 volts RMS, 60 hertz, but the 60 hertz doesn't really matter for this problem. 2 ohms. Here's my transformer. 10 ohms. And then here's my R load. And this is 1 to 20. And this is N to 1. All right, and what do I tell? Well, we know the power going into the load. Power going into the load is no. I know what that is. That's what my check mark here. I know what the power going into the load is. And since I know the resistance of the load, then that means I can find either the current of the load or the voltage going into the load. Either one I know, because I know the power going to the load, of course, is I load times I load R load, where this expression here would be the V load. So I can find, I know the current over here. So let's work with that. So I know I load. I know that current. Well, if I reflect this I load across here, using the turns ratio, I will have then an expression for I line in terms of N. I can then reflect that I line across here, using the relationship or the relating current for the transformer, to get my IS. Now this IS is going to be a function of N, because even though I load is known as a number, I line is going to be a number multiplied by some term involving N. And so IS consequently will also be a function of N. So that's one way I can translate the currents all the way across. Now I could do the same thing with voltages. However, you have to be careful. This voltage here, or more specifically this voltage here, call this some V1. V1 does not equal 100 volts RMS. It just does not equal that. So if you were to try to reflect this voltage across, you can't find V2 from 100 volts RMS. You can't just reflect 100 volts RMS to get V2, because you have a voltage drop across this 2 ohm resistor. Very common mistake. Don't do that. And so anyway, so we can take the load current that we know, reflect it across, get I line as a function of N, reflect it across, get IS as a function of N. So that's one way to get IS. But we also know that IS and VS have to be related by the impedance. And so another way I could get to IS is, here's my 100 volts RMS. Here's my circuit. Here's my transformer. And so this would be the 10 ohms, 2 ohms, where I generate a new impedance here, call it Z load prime, and Z load prime is going to be a function of N. R load is known, but if I reflect this across, that Z load prime is going to be a function of N. And so this obviously still is going to be a function of N. Then I can add these two together, add them up, reflect them across, and get then a new equivalent circuit here. Here's my 2 ohms, and I'm going to call this Z load double prime. And this has to be 100 volts RMS. And so now, Z load double prime is going to be a function of N. And I can use this then to develop an expression for IS. That's a function of N, because I can take 100 volts divided by the sum of 2 and Z load double prime. So this IS is going to be a function of N that was derived based on reflecting impedances. This IS I can develop from reflecting currents, and I know they have to be the same. So I set them equal, and that will allow me to solve for the turns ratio N. Once I have that, in this particular case, I'm going to have two roots. I'm going to have two different possible values for the turns ratio. Once I have those two different possible values of the turns ratio, I can then use that to find two different values for the line current and two different values for the power from the source. But you're told, assume that most of the power from the source is delivered to the load. That means we want the power from the source to be as close as possible to the 800 watts. It has to be greater than, unless you made a mistake, obviously. So you pick the smallest value of the power from the source. And the value that corresponds to the smallest value from the power from the source is going to also correspond to the correct turns ratio and the correct current subsequently. So that's how you want to solve it. Now you can also solve this with reflecting voltages, but you have to be very careful with this voltage handle, how you handle this voltage. But at the end of the day, it would be a similar process. You could reflect the voltage across the load, which you can also find, get that in terms of N, and then it gets a little messier at that point, but use that instead of perhaps maybe the impedance. But I would recommend the current. So reflect the current I load current to I line. I line is a function of N. Reflect it across, get IS as a function of N. Then do the impedances and find a function of IS in terms of N, and then set those two values of IS equal. So the only other one that I have gotten questions on thus far is on problem 5. And problem 5 is identical to the in-class example, so I'm not going to go through it. One change is obviously it's the non-ideal transformer is connected directly to the 10 kilovolt source and the 10 ohm loads. There's no other like line resistances are in there or something. That could be a point of confusion, but there's no line resistances in that. So problem 5 is just the identical to the in-class example. And so let me confirm that we don't have any other questions that have come in since then. Nope, so that's all the questions I've gotten so far. And so we'll go ahead and stop there so we can get these things posted and give students an opportunity to learn from them.